Okay, hello. I hope the voice is clear. So let's start and recap what we have done so far. So in previous class, we studied about vector spaces. Vector space. What it is just a vector space is a set of elements. Okay, and we abstractly denote them by that this is V and this is abstract notation for a vector. Okay, so over a field f, okay, a field f, and what is a field? A field is just field, I mean field, let me write it. Field f is just set of scalars, okay, with which is closed under algebraic algebraic operations, okay. And you know what are these algebraic operations? That are addition, subtraction, division, these kind of, they all, these scalars follow these operations, okay. So a vector space is just a set of elements abstractly denoted by cat, okay, over a field f, okay, following some axioms, following some 9 to 10 axioms. And okay, in in the book you in the book by R Shankar, if you have read, he just says that you don't have to memorize these kind of axioms. You just remind, or you just recall, try to recall, and whatever comes into mind, just write it down. So what kind of axioms you have studied in mathematics? Normally we have many kind of things like suppose commutativity, right, associativity, or closure properties, and distributive properties. What else? Can be inverse, can be identity. So these are the things we usually study in mathematics. Okay, so there are two operations, or two functions. uh, First is like binary function, okay, binary function defined as, uh, you can, like, yeah, you can denote it like this: a binary function from field f cross v, vector space to vector space, okay. And there's another, it is a binary operation, it is a binary operation which can be given by from v cross v to v. So binary operation is also a function, okay, but it takes the values, input values from the vector space itself, and uh, it takes the value from vector space, and output is also of the vector space, okay. So this gives you an ordered pair from same vector space, uh, ordered input to a function is ordered pair, and uh, output is also output from a set, and output is also in the same set. Okay, so such functions are operations. So operations are done within the set itself. Okay, operations are done within the set itself, and a function can be from different for different sets. Like f is a different set. It is a set of scalars. It is a set of vectors. It is a set of vectors. So it is taking from ordered pair from different sets. Okay, but it is an operation in which the input is from a set and output is also from same set. Okay, so we just do have these two kind of functions or operation. Okay, so okay, so yeah, of course, for commutativity there is only one axiom. For associativity there are two axioms. It can be for there are again two axioms. Okay, why I am taking those two? One for this, one for this, one for a function. Okay, and of course, yeah, what is that binary function? It is a scalar multiplication. Scalar multiplication, okay, which is a multiplication of a scalar from field and a vector. Okay, and similarly, binary operation is the vector addition. Vector addition. Okay, it is the addition of two vectors. So of course, here binary means input is two. Input is two. That's why we are calling it binary function, binary operation. Okay, so commutativity only contains the binary operation. Okay, it do not contains binary function. Associativity both contains both scalar multiplication and vector addition. Closure property also contains both for both for scalar multiplication and vector addition. Distributive property is also for both. Inverse is for one and identity is for both. Okay, so how many are there? In total, we can fix the number of axioms to be 10. Okay, these are 4 into 2 is 8 and plus 2 is 10. Okay, so what are these? Okay, I will just talk about why why don't we include other, like why there is only one commutativity and one inverse. Okay, so commutativity is only for scalar sorry, addition. Vector addition. Okay, so such that if this is 1 plus this is 2, okay, so this will also be applied. So this is only for vector addition and scalar. mm, just a second. Okay, um, so yeah, so there is no such thing like there's no such thing we assume like this, or like no such thing like this actually. Okay, this is simply as this. We assume that they are same thing, and we assume that it is just a different vector. It is just a scaled vector. Okay, it is just a scaled vector. Okay, which belongs to our like vector space. Okay, so in quantum also you just see that also the scaled vector and the simple vector are same physical states. Okay, and physical states because these coefficients do contribute to the probability density only. Okay, it tells you about the density probability of the particle, but the particle is in the same state, that is equivalent. These states are equivalent. And here also we take that scaled vectors are equivalent. There is no property for these scalar multiplication. Okay, so it only applies for vector addition. And secondly, there is only uh, which identity? There is only additive inverse. Yes, do only exist. Okay, yeah. So additive inverse is, so this is taken to be additive and inverse, and when you add it to any vector, okay, it will give you the same vector. Okay, so this is my additive inverse for all v belongs to vector space. And why there is no such thing as additive, sorry, multiplicative inverse, multiplicative inverse, that is uh, there is no such thing as vector inverse thing. Okay, so this will be from a different set then. Okay, uh, in our set, in in our set in vector space, we do not include such thing as vector inverse. Okay, yeah, inverse vector additive inverse can exist like this. Okay, so yeah, so this is the thing. You can read in books these kind of things. So you can of course write commutativity for binary operation, that is vector addition, and associativity for both, closure for both. You can just prove this, and these are 10 axioms, and the objects which follow these kind of axioms are vectors in general. Okay, so let's move ahead. Suppose let's there is a question. Okay, let's prove that the set of all linear combinations. Okay, I could not just find a better explanation for these two things, that why no such things can uh, are taken in this axioms. You can find it in the books very well. I just find these kind of things. Okay, so that's up to you. You should find it. I mean, if you know that there are only two things absent from this axioms, then you can remember all of these. Instead of memorizing all of these axioms, just try to recall that what were the properties that were not included in the definition of vector space. So it becomes easy to remember or recall the all axioms. So prove that the set of all linear combination of partial derivatives, okay, partial derivative, sorry, partial derivative operators, okay, form a vector space. Okay, let's prove it. Let's try to prove it. Try to prove. Okay, okay. So let V. Uh, okay, let's. Okay, yeah. Let V is a set that is my vector space from I running sum over I to, like, suppose you can take from 1 also. So this is my partial derivative. Okay, why I'm taking linear combination? Because in vector space all the vectors are connected, okay, through the this linear combination. You can uh, I mean, you have just proved in the previous class also. I have just mentioned that you can um, combine vector spaces linearly. Okay, we can just prove it. It's a short exercise. So let this vector space be the linear combination of these partial derivatives such that these scalars that are ai belongs to, this is real space, okay, real numbers, and this is my field. Okay, this is my field. So it is defined over real space. So suppose let's prove the axiom first. Okay, try to prove the axiom first, that is closure under vector addition. Okay, so try to add two vectors. Suppose there exist x and y belonging to these, okay, such that x is equals to summation over 1 to n ai del xi. Okay, mm, not summation actually, this is just suppose one of the vector, and suppose there is another vector, that is y, let it be capital Y, and bi xi. Okay, there are two vectors here, and you just try to add them. Okay, let x plus y is equals to a d plus b I dxi. You can take it out. Okay, now since ai plus bi belongs to r, okay, so this means x plus y, that is this, will also belongs to this, because this is again a scalar. Okay, because a field follow all algebraic properties, right? Algebraic properties, from those you can write this. Okay, so this is again a real scalar multiplied by this partial operator, partial derivative operator. So again this will be inside this vector space, so it is closed under vector addition. The second axiom is closure under scalar multiplication. Okay, so again, let's try. There are 2 and y equals b. This is b. Okay, this is xi, and they both belongs to vector space. Now, uh, sorry, do a scalar multiplication, not the multiplication of vectors. So let's try. This is a scalar. Okay, let me write it. This belongs to my field, and let's multiply it with a vector, and that will be c multiplied by this vector, and again this will be equals to this. Okay, and since this again belongs to my field, this implies that this will also belongs to my vector space. Okay, let's try to prove the third property. Okay, I will not prove much of these properties, but let's do this one. Axiom third. Let's do the associativity. Associativity associativity of vector addition. Okay, so if we have uh, okay, wait a second. So I should take the summation here. Okay, let's take, yeah, that's why that then it will be a vector. Yeah, when you take these summations, then I forgot that we are not doing an Einstein summation, so this can be like this. Okay, so this belongs to V. You can do this. So again, you take 2 vectors like summation over this. Okay, and another vector that is, let's take its scalar as bi, and a third vector, let's take this as ci dxi, and they all belongs to vector space. Okay, so let's do this. Let x plus y plus z, you compute this first, and that will be ai dxi, okay, plus bi dxi I, and you compute this first, and then there will be ci dxi. Okay, so what will happen, you can just take these, you can just write it like this is bi and dxi. Okay, dxi plus then ci dxi. Ah, of course you know that you can add it again and take the partial derivative out. This will become like this. Okay, so of course this belongs to vector space through because we have already proved that it is closure under vector addition, so it will belong to the vector space. Now try to add this opposite way. Okay, you can find that it, it is easy. Okay, so you just do this. first, and then you will find that it will be same as this. And again it will belong to vector space, so they are equal. So this follows associativity also, associativity and the vector addition, and you can just do for do for all axioms, hence proving that we proved that uh, we proved that the set this follow all axioms of a vector space. Okay, follows all axioms of vector space. Therefore, the set therefore the set V is a vector space, and its element are its element are called vectors. Okay, now you know what was the vector. It was like this. Okay, it was like this, and when suppose my a1 is 0. Okay, uh, I am just confusing the this upper indices and lower indices. You can just make it like lower or upper, but usually we do write like this. By convention I should write it upper indices. We will get to it what is upper indices and what is lower indices, but first let's suppose my sorry, let's remove this also and write it in the upper indices. So let's take the first to be 1, not 0 actually. This is first component to be 1 and all others components to be 0 such that it is not equals to 1. Okay, so what will happen then, is this will be x1. So this is just a partial derivative, partial derivative. Oh great. So what we do see, what did we see is, what did we see is this. Surprisingly we get that all partial derivatives are vectors, actually vectors forming vectors in a vector space, over real numbers. Okay, that is my field is of real numbers, then all partial derivative. You can check that it can also be applied to field over complex numbers. So partial derivatives are actually vectors. Okay, all partial derivatives. So we can notation shorthand notation for partial derivatives. Okay, we will see that this is given by this when this is taken as upper indices and this is taken as this when the indices are 0. We will see that. We'll see what does the placing of indices be. Okay, so you can just see they are, I mean, vectors. One of them is vector and one of them is dual vector. We will also see what is a dual vector now. Okay, so yeah, and a basis in such coordinate vector space is known as coordinate basis. That is known as coordinate basis. Okay, these are known as coordinate basis. Let's just move to define what is a dual vector space. Okay, dual space abstractly denoted by this thing, this model. So it is a set. It is a set of linear maps. That is V star such that it takes an input from vector space to the field. It is a vector space, okay, and it is a field over which the vector space is defined. Okay, simply it means it takes it takes a vector as input and gives output as scalar that belongs to a field. Okay, so dual space is a linear map from a vector space to a field. Okay, so okay, you can also check that uh, dual vector space a dual vector space is also a vector space is also a vector space since has follows it follows or say its elements follow all axioms of a vector space. Okay, it follows all the axioms of a vector space. That's why this dual vector space is also called as the vector space. I mean, this is also a vector space. Okay, it is just a vector space, but it is a set of all the linear maps that takes an input from the vector space, that is a vector, and it spits out a scalar that belongs to a field. Okay, so yeah, elements of dual vector space can be abstractly denoted by a bra that is like this. Okay, this like this, and are called one forms. Okay, these are called one forms or say covectors. Its elements, the elements of dual vector space are called one forms or say covectors. And there are different names actually for dual vectors. You can call like them simply as dual vectors also. There are many names like these are also called as covariant vectors. Uh, but it is by the transformation properties we will see that. So the elements we have defined a dual vector is just a set of linear maps. Okay, and it is also a vector space because its elements do follow all the axioms of the vector space, and its elements are denoted by this bra notation and are called the one forms. Okay, so of course you have studied in QM these kind of things, that this vectors, this is a vector, okay, or say a cat vector, okay, and this, sorry, this is a covector, or say you usually say this dual vector in quantum mechanics. This is a bra vector, okay, the this is a bra covector actually. Okay, so these are the things. Now, okay, this is a vector, and what is the vector space? It is a P is a Hilbert space, Hilbert space, okay, which is a which is a complete vector space over complex field. Okay, complex fields means complex numbers. Okay, you have studied that complex numbers. Let me erase this. Okay, so it forms complete here means that you can study this in your book. What is the meaning of complete? It is actually the convergence of Cauchy sequence. Okay, you can define a Cauchy sequence and it should be convergent. So this is the Hilbert space, which is a vector space. Okay, so yeah, and we will see uh, like all one forms are yeah, we will see that these are dual vectors or say co-vectors. Okay, yeah, let's move ahead to define something. Okay, so we shall now show that given a basis, given a basis that is a vector basis denoted as this, okay, and of vector space. Okay, this basis belongs to a vector space that is V. Okay, curly V. We can find, given a basis of vector space, we can find a class of one forms. What are one forms? These are just elements of dual vector space. Right? That are, it is elements dual vector space or dual space. Okay, we can find a class of one forms that is denoted by, this is omega. Okay, and this is, you can write it like this. This is my class of uh, okay, let's not denote it by Brian Cat. Let's denote it like this only. Okay, this is a set. Okay, this represents a vector, our usual vector. Okay, and this represents some kind of surface. Okay, this represents some kind of surface. This is a curly bar over omega, or you can call it w, small w. Okay, so this is my class of one forms. Okay, such that such that this curly thing, this base, this one forms, take the inner product, and you will find that this is assumed. Okay, this is assumed, or say given to you. Okay, we shall now show that if you have given this basis, and we can find, so we can find a class of one forms that are elements of dual space, this such that this inner product is given between both, and then this class of one forms then this class of one forms a basis constitute a basis for the dual space. Okay, the V star space. We just have to prove, okay, we just have to show that if we have given this basis in the vector space, we can find a class of these one forms, or say covectors, that are elements of this dual space, such that this condition is given to us. Then we will show that this class of one forms will constitute a basis for this dual space. Okay, so suppose proof. Okay, suppose the class of one forms, okay, are linearly dependent. Okay, we just assume a counter example of it, a counter situation, that let's firstly take this class of one forms are linearly dependent. That is, what does we mean by, what do we mean by linearly dependent? That there exist scalars. Okay, this is lambda mu, these are scalars belonging to the field. Okay, of course, the field, that are not all zeros, not all zeros, not all zero. Okay, such that let's take this condition. I mean the condition for linear dependence, that is these scalars. Okay, and these are one forms. This is zero for I mean some of them can be zero, and some for they are non-zero for some I. Okay, and this mu, or say, okay, so we can just multiply both sides by Okay, take the inner product by this. I will show that why are we taking like upper indices and lower indices. Why are we assuming that I will like have patience for it. Mm, you just you just write it down now. So this is the thing. Okay, now this can be distributed as like this, and this is 0, and this will be okay by the condition we have given. This is mu. Well, of course it should be, because there is a summation of mu already. I should multiply with a e nu. So it will be orthogonality condition. This, let's mark it equation first. Okay, so using first. Okay, so you can just see that the summation will be cancelled, and there will be only this, because the delta, when you sum over it, the delta will be 1 only for this is equals to this, and it will be 0 for all not equals to mu. Okay, mu not equals to mu. So this summation will give out only the new component, that is this. Okay, so this condition apply for all nu equals to 0, 1, 2, 3, whatever dimension you take. Okay, so hence this class of one forms. Okay, remember that one forms are the elements of dual space satisfying equation 1, that is condition 1. Okay, this one condition, orthogonality condition, are linearly independent. Of course, you have studied this in quantum mechanics course, that when the coefficients of any basis are all 0, then they are linearly independent. Okay, coefficients of these vectors. Okay, if and the coefficients of these vectors are all 0, they will all the vectors will be linearly independent. And if they are, we have assumed that initially that they are all non-zero, not, I mean not all, but some of them are non-zero. So we assume that they are linearly independent. But by this application, okay, multiply or take the inner product, take inner product or dot product, whatever you want to say. Okay, or dot product with, this is my basis. Okay, this is a vector, unit vector. So we found that these class are actually linearly independent. So, and hence uh, these constitutes, which the class of these one forms constitute the basis, hence a basis for this dual space, because they are all linearly independent. All linearly independent vectors do form a basis for any vector space. Okay, and since this dual vector space is also a vector space, uh, these will this will follow the same rules of vector space. So also, let now let assume that this vector belongs to this dual vector space, and mm, yeah, so multiply this with a vector of this, and you will get, I mean this is just a projection of this dual vector onto this direction. Okay, and you will find a component of it. Okay, like this. Okay, let's zoom it this as only like this only, not with the curly. Let us just take this curly for the basis vectors only, and this cap only for basis vectors. Okay, so this component in this direction, mu direction, will be given by this. You just take this inner product. It is similar to like taking like I cap with a like dot product. Why you have studied this already. Taking the I cap dot product with a general vector, it is like this. Suppose this is my general vector. Okay, and you take a dot product in the I cap, you will just find the component in the I cap direction. It is similar to this. Okay, so you now understood this. Okay, so now also you take summation over mu and this thing, and this is my basis vector. This is basis covector actually, or say one form, and you take a dot product with this. Okay, and you will get, what you will get is summation over this, and okay, not this, not this. Okay, so you will get, of course, from using one first condition, again you will find that this summation will be delta, Kronecker delta, and it will be only uh, non-zero for mu equals to nu. Okay, it will be only non-zero for mu equals to nu when you expand this summation. Okay, because for all mu not equals to nu, it will be zero. Okay, so this will be equals to like mu will get to mu equals to nu. So this will be the summation. This is my covector, sorry, yeah, covector basis multiplied by. So you just have two equations now. This is my equation second, suppose, and this is my equation third, and you just compare both. Okay, you can just okay, you can just write it like this also if you want. Exchange the indices. Okay, this is my nu. Okay, this is my mu. So now you can better compare it, because you can, these are just dummy indices. Okay, you can just replace it with mu or nu or whatever you can write it. So now you can compare it both, and by comparing you get what you get. By comparing we get that this dual vector, or say one form, can be given as its component form as like this. Okay, since these are dummy indices, I am just writing it into mu indices. Okay, this is the thing. Okay, this is the, it is the linear expansion of one forms on the basis of this dual space. Okay, it is similar to this, similar to our vector, similar to vector case that we used to write that any vector can be written as linear. Okay, I should write it as summation over mu. Okay, so any vector can be written as linear combination of its component, and let clearly, so this mu and this nu, mu again. Okay, and this is a cap. This is for vectors. Okay, this is linear combination, linear expansion. Okay, of a vector in the basis, this of vector space. Okay, you know this, and we have proved that in the dual space we can also expand our covector or say one form or say dual vector and its linear combination of the basis defined in this dual space. Okay, and you just notice, okay, just one thing. Okay, so these are the components of one form. Okay, and this is the basis in dual space. Okay, and this is a one form or a covector one form or dual vector or say a covector, whatever you want to say. Okay, so now, yeah, this basis, which basis, this dual basis is called a dual basis actually of this basis in vector space. Now, often vectors, that is the elements, and what are these elements, these kind of things abstractly, okay, of vector space. And what is that vector space denoted by curly mu, curly v, are called contravariant vectors. Okay, this is actually due to the transformation properties that these vectors and covectors actually do transform just oppositely. Okay, you can just prove that they do transform in any transformation, they do transform oppositely. So that's why their components are like usually denoted as this, and oppositely their basis. We will see that how the bases are different from the components. Okay, and but you just see in overall, like, covectors do transform oppositely. Okay, that's why we do denote the vectors within the components of the vectors with upper indices, and the components of covectors or say one forms of whatever dual vectors, okay, with the lower indices. Okay, uh, so since the basis of covectors do transform opposite to the this component, that's why we write the the indices for this basis one forms opposite to the this convention. Okay, you can just choose any convention that writing, like for covectors you can just choose the convention that you write the components with the upper indices and the basis vectors are low with lower indices. You just have to choose for it, but you have to again change it here also, because they do transform very oppositely, because they live in different spaces. Okay, and they transform in different sense. So according to the transformation properties we can see an example, okay, in next class maybe, that the vectors are the elements, are also called the covectors, sorry, contravariant vectors, and are and its components are generally or usually are usually denoted sorry denoted by mm, like this, with upper indices, with upper indices. Okay, and covectors, or say one forms, okay, that are elements, that is double of dual vector space denoted by v curly star are called covariant covariant vectors. Okay, they are called, also called covariant vectors because of their transformation properties, and its components are usually denoted by this kind of thing with lower indices. Okay, so whenever you find such thing, okay, any component, suppose you find any component written like this, component written like, suppose this is my a mu, so this is when it is, the indices are on the upper stage, upstairs. Okay, this is called a contravariant vector. Contravariant vector, it is, you can just call it a vector, you assume these are just components of a vector, normal vector. Okay, but when they are written like in the lower indices, lower stage, lower I mean downstairs, okay, then these are called covariant vectors in tensor calculus. Okay, so this is how we define things. So this is how we define. Now let's move to something geometrical thing. So, sorry, geometrical interpretation. Okay, so we can write this. The geometrical interpretation of a vector can be given by arrows. Okay, by arrows, that this is a vector. Okay, so we can just write it like this, that this is a vector. Okay, like this is a vector, and it's, of course, you can write this vector with components like with upper indices and its bases with lower indices. Okay, and and of a covector that with one forms can be given by planes, okay, or surfaces. Okay, so there is a surface, you can just, okay, this is a surface, and you can just call it sorry, you can just denote it like this. Okay, uh, I mean abstractly you can of course write this as uh, cat and this as brown, and you can also write this because this notation is actually for surface. Okay, notation, so you can just write it like this also, simply that mu with lower indices and its basis will be given by this upper index. Okay, so this is how you can write it. Okay, also now let's introduce one more thing, that is inner product. Inner product. Okay, inner product is given as the, not you can write it like this. Okay, and you can of course expand it. You know that the the covectors or the dual vectors are expanded as this. Okay, with a dot product or say inner product, you write it like with different indices, and this is v for vector with upper index and written like this. Okay, so you can uh, write more compactly as mu summation nu, and this is new of course. So yes, let's write it. Wait. So this is new, and this is also new. Okay, now take the dot product of it. Okay, and you know from this first condition, from the orthogonality condition, this is delta mu nu. So there is a summation. Okay, so you have this component and this vector component, and there is a delta mu nu. Okay, so what will happen, that delta mu nu will cancel out one of the summation, because when this when the summation one will run over one of the indices, suppose nu. Okay, then it will be non-zero only for nu equals to, it will be 1 only for nu equals to mu. So mu summation will survive, and this will be mu. Okay, this will happen to be mu, and this is, you know that this is simple inner product condition. You have already studied in your quantum classes. Okay, so this is the inner product condition, and of course this inner product gives you a gives you a real number. So you can see that how, you can see now that how a dual vector is actually a linear map, a linear map that takes one vector one vector and give out a real number, or say the, if your field is of complex number, then it will give you like a complex number. So better we should write it as like scalar. It gives you a scalar, and scalar are always invariant, and in all the experimental things, the output data is only of scalars. So we need to like convert all of our theory, whatever quantity, physical quantity you are constructing, maybe it is of tensor or vector or whatever it is, you should be able to convert it into a scalar quantity. And this is how, taking inner products, you convert them, taking the linear mappings. Okay, you convert them to a scalar that is in invariant quantity, and a scalar do not depends on any coordinate system. Okay, so this is a very important thing. Okay, so you can see that a dual vector takes is a linear map that takes one vector and give out a scalar. Okay, belonging to any field. Okay, it gives out you a scalar depending on what field you are considering to like define your vector space. Okay, that's it. And oh yeah, one more thing, that geometrically, how can you interpret this? You can interpret this, you can interpret inner product as number of number of planes or surfaces, okay, skewed skewed by an arrow. Okay, so of course the planes are one forms or say covectors, and an arrow are vectors. These are one forms, or I should write it covectors so that you can remember it. Uh, but one forms are better option to write it here, because in differential geometry you can define one forms like this. Okay, so and an arrow is just a vector. So if there is a set of planes, if there are set of planes like this, okay, okay, so that's how I think. Like let's remake it. The different planes. Okay, so these are planes or one forms. Okay, and there is an arrow. Okay, sorry, that's an arrow. I should not go like this. So there's arrow. Yeah. So this is an arrow. Okay, this is a vector. Vector. Okay, so you can just interpret inner product like this. Okay, geometrically, an inner product is the number of planes squared by an arrow. Okay, that's it. So that is the thing. We need the notion of dual vectors, or say covariant vectors and contravariant vectors. How do they transform in the future classes? So, yeah. Okay, thank you.